what we're going to talk about now are the function interface of Java functional interfaces. And you'll see that this is just a slight variation on the predicate that we looked at a second ago. So the main difference between function and predicate is that function has a return value that could be something other than Boolean, whereas predicate has a return value that's always a Boolean. So you can see function's a little bit of a generalization of what predicate was. So that's why we describe predicate first. So function is going to apply a computation on a single parameter and then return a result, which could be of some arbitrary parameter. Of course, it has to be decided when you instantiate the generic function, or when you implement it. So it's a generic interface that's parameterized by two reference types, the type that's passed as the parameter and the return type. And then the apply method is simply going to have an abstract method that's passed as a parameter, passed a parameter of type t, and returns a value of type r. Okay, so far so good, hopefully. So let's take a look at an example. This is actually a really, really fun example. This is in my EX9 folder. And what this does is this creates a cache, which is also a concurrent hash map, that's going to map integer to integer. And we're going to use this in order to cache the results of prime number computations. So imagine you had a large number of numbers that were large, or potentially large, and let's say they're random, and you want to figure out which of those numbers is prime. Well, there's various ways to do that. One way to do it is to check each time someone gives you a number that might be a prime. Let's call it a candidate prime or a prime candidate. You'd run this algorithm to check to see whether it was prime. But that would take a fair amount of time, especially if the numbers are large. So what we're going to do instead is we're going to make a cache using a concurrent hash map where we compute the value, we compute whether a number is prime or not, store the result into the map as the value where the key is the number, the prime candidate, and then next time we want to compute whether a number is prime or not, we're going to look it up in the map first. And only if we don't know the answer, and only if we haven't pre-computed that value before, do we go ahead and check to see if it's prime. So that's the basic idea. It's a cache. It's a cache of prime numbers. The way we're going to implement this is by using a super cool method that's defined on concurrent hash map called compute if absent. And what this does is it checks to see if there's already a value associated with a given key. In other words, for a given prime candidate, do we already know if it's prime or not? And if it isn't already known, it calls a function to compute the result, stores the result into the map under that key as the value, and then returns the value. So that's basically what compute if absent does. And compute if absent is a really cool method that supports so-called atomic check then act semantics. You can read more about atomic check then act down here at this link. So basically what it does is it'll work in a multi-threaded program correctly and efficiently, even if multiple threads simultaneously in parallel call compute if absent on the same key, on the same prime candidate. It'll only call the function one time, and it'll handle all the synchronization in a very clever way. What's interesting here is this second parameter to compute if absent. The first parameter, of course, is the prime candidate, whatever we're trying to check to see if it's a prime number. The second value is the function that we use to convert or to check whether the key, the prime number, is prime or not, and if so, it stores that value into the map. So that's the prime checker function. And you can see the prime checker function down here, whose code I omit at the moment, takes an integer, which is the prime candidate, and returns an integer that's 0 if the number's prime, or it's the smallest factor if it's not prime. So that's a function, mapping a value to a value. You can also pass in a method reference here as well. So you can either pass it as a lambda expression, or you can pass it as a method reference. I kind of prefer this approach here. It's a little cleaner. And as I mentioned before, if you're in Android Studio or IntelliJ or some other modern interactive development environment, some other modern IDE, it'll automatically perform that comparison for you, or that transformation for you. Okay, so now that I've kind of introduced this concept of a function, let's take a look at what compute if absent looks like. So if you were to poke around in the source code of the Java development kit, you would see the compute if absent method that's defined on the concurrent hash map class. And you can see that compute if absent takes a key and a function, which in this case we call mapping function, or it calls mapping function. And you can see deep in the bowels of the code that what it's going to do is it's going to go ahead and apply this mapping function if the value doesn't already exist. So we go and look up in the map to see that we already have a value. If we don't have a value, we're going to go ahead and apply the mapping function, calling the apply method, on the key, get a result back, and then update the map. So let's kind of break this down and see what's happening. It's kind of interesting. Oh, and I should also mention that this is done atomically. One of the great things about the concurrent hash map is all of the methods are atomic in a very efficient way. We have a little bit more syntax. The question mark, super K, is what we looked at before. Super is a lower bounded wildcard that restricts the unknown type to be a specific type, or a super type or parent of that type. You can read more about that here. Extends is a so-called upper bounded wildcard that restricts the unknown type to be a specific type, or a subtype or subclass of that type. Again, that's just Java syntax dealing with generics. These keywords play slightly different roles in Java generics. You can read more about that at this link. Okay, so let's take a look at what we're actually going to bind this stuff to. So the mapping function for our example is bound to prime checker. So prime checker is the method reference we pass in here. And so that's what's going to be the mapping function for what I'm about to describe. And you can see what happens down here is that if the key doesn't already have a value, in other words, if you look it up in the table and it returns null, then we're going to apply the mapping function to the key. And here's what that looks like given the mapping function binding. This will basically be if val equal prime checker key. So it's going to go ahead and replace apply with the call to prime checker. So once again, you can see how the apply method is kind of logically replaced with the prime checker lambda function. And you don't have to define an anonymous inner class of any form that has a method called apply. You simply have to provide a method reference or lambda expression that matches the function descriptor of the signature of the function interface. Okay, any questions about that? Very powerful, very concise. This is cool for all kinds of reasons, part of which are functional programming, part of which is the cleverness of how the Java concurrent hash map is implemented under the hood. Here's another example, perhaps a more powerful example of a function. And this one, again, is going to be in the context of our Three Stooges. It's the EX5 folder. Here we're going to create a list of threads where each thread we give a name, Larry, Curly, and Mo. So we have a list of threads. And then we're going to print out the threads. First time we print it out, it'll say Larry, Curly, Mo. But then we want to sort these things by their name. So we're going to sort them by using the comparing method of a comparator using thread : get name to sort the threads. And we'll talk more about get name. Get name is just a method that takes, it basically returns the name it gets the name of a thread and returns that. The comparing method here uses the parameter, which is a function, to impose a total ordering on some collection of objects. So if you go and look at comparator comparing, it's going to essentially perform a comparison, and that's exactly what the sort method needs to do its thing. One of the other cool things you can do here is you can have a way of comparing things in reverse order. So if you compare in reverse order, it'll sort with basically Mo, Larry, Curly instead of Curly, Larry, Mo. So you can reverse it quite trivially. So here's what the comparing method looks like. So you can see comparing is a method that's defined in the comparator interface. You can read about it down here in this link. Comparing is used to impose a total ordering on a collection of objects. It takes a function, functional interface as a parameter, which is given the name keyx for key exchange. And you can see that that gets mapped to thread : get name. That's what we actually pass in. Back here, we're passing in this method reference, which is a function, to comparing. And that's what gets bound to the keyx parameter. And then here's how this thing actually gets used in the code. So if you take a look, comparing says return C1, C2, and C1, C2 in this context are the thread objects that are being compared by sort. Remember, if you step back a second, we've got basically a list of thread objects. So that's what's going to be compared, the thread objects. But we want to compare them based on the names of the threads. And so you can see what they're doing here is taking the apply method, so key X apply, passing in the thread object, and that's going to return a string. So we're mapping the thread object to a string. And what this turns into, if you were to think about how it would all be expanded, it would be c1.getName.compared to c2.getName. So essentially, we're comparing these things, and that's kind of what it looks like. So we're comparing the names with each other. OK, just to show some other interesting things, you can also compose functions, just like you can compose predicates. Here's kind of a little interesting example of using this. It's kind of silly, but it illustrates the point. We're going to have a class called HTML tag maker. And what it's going to do is it's going to have methods that prepend less than and append greater than to a string. So given a string, it'll turn it into an HTML tag. Marginally useful, illustrates the point. So what we're going to do here is we're going to go ahead and create a function called less than, which is going to be the add less than function here. And then we're going to make another function which is going to say less than, which is this guy, and then add greater than. So we're basically creating a function that's going to compose together two operations. So and then composes two functions together. And then we're going to go ahead and do this, where we're going to say tagger, this guy, tagger.apply HTML plus tagger.apply body plus tagger.apply /body plus tagger.apply /HTML. And this particular expression will generate this string. So it'll print less than HTML greater than, less than body greater than. So you can see it does that. Yeah? Because tagger is an object and you need to call a method on it. So we need to say what method we're calling. So recall that a function has a single method called apply. And so in this particular case, we need to make that explicit. This down here, by the way, is not a Lambda expression. This is just calling a method on an object. You could refer to the, if you were using tagger as a method reference, you could omit the apply. But in this case, you need to say apply, because tagger is an object. So we say tagger dot, call its method apply. Tagger is an object of type function. Question? Yeah. Oh yeah, I was just trying to make it so that you could see, less than dot and then. So just composing. This is just illustrating we're composing together these things. There's other ways to write it. I was just trying to make it clear. Cool. Any other questions about that? So that's just illustrating how it's possible to compose functions together.